Hi guys, today we'll be taking a look at trigonomic identities for the Capital Area Math League. This video will be an introduction into the subject, so once you're done watching this video, or if you are already proficient in the subject, remember to try out the problem set linked in the description below, and remember to compare your solutions with the provided one, because that is where you are going to solidify those basic concepts and also build up speed for the actual meet. The trig identity round is broken into two parts. The first is the memorization of those trig identities, and the second is their application, and it is the linkage of these two processes which make up problems in the round. Trig identities are equations that involve trig functions like sine and cosine that are always true no matter what values our variables are. Now normally, a trig function would take an angle theta of a right triangle and output the ratio of its sides. For example, sine theta in this example is equal to b over c. But I'm going to use a different model to describe trig functions. Consider on the coordinate plane a unit circle of radius 1 centered about the origin. Now place a point P anywhere along the circle. Now construct a radius 2 point P, and that radius must make some angle theta with the positive x-axis. On the unit circle, trig functions are defined as the following. The x-coordinate of point P is cosine of theta, and the y-coordinate of P is sine of theta. There are a few other basic trig functions. Tangent of theta is equal to the slope of the radius 2p. It is equal to sine theta divided by cosine theta. There are also reciprocal functions for each one. Cotangent of theta is equal to the reciprocal of tangent theta, secant theta is equal to the reciprocal of cosine theta, and cosecant theta is equal to the reciprocal of sine theta. It is very important to note that each function can be expressed only in terms of sine theta and cosine theta. We can exploit the idea that cosine theta and sine theta are the coordinates of P by tracing when they are positive and negative through each of the four quadrants as shown. For example, in the first quadrant both are positive, in the second, cosine is negative while sine is positive, and so on. The reduction identities enable us to simplify the angle within a trig function. For example, what would happen if we rotated theta an extra 360 degrees? Well, we can see here that P lands exactly where it had started originally. Therefore, theta plus 360 degrees in any trig function should give us the same output as if we had theta. And similarly, we can investigate what would happen if we just rotated theta by an extra 180 degrees. We can see here that the slope of the radius 2p is the same as before. So we conclude that tangent of 180 degrees plus theta is equal to tangent of theta, and a similar thing for cotangent. What if we added an extra 90 degrees to theta? Then by a similar method, we can conclude that sine of 90 degrees plus theta is equal to cosine of theta, and so on. What happens if we negate theta? Taking negative theta is the same thing as saying that you are reflecting across the x-axis. And because sine theta is the y-coordinate, sine theta is negated. But because cosine theta is the x-coordinate, it doesn't change, it remains cosine theta. If you compared 180 degrees minus theta to theta, that is the same thing as reflecting point P across the y-axis. Because cosine theta is the x-coordinate, cosine is negated. But because sine theta is the y-coordinate, sine theta remains. Now with the unit circle, we have no need to memorize these reduction identities. If we just investigate to see what happens when we change theta, we can derive the identities ourselves very easily on the fly. You may have noticed that on our unit circle we have a right triangle with sides length sine theta, cosine theta, and the radius of 1. If we apply the Pythagorean theorem to this triangle, then we obtain the Pythagorean identities. Sine squared theta plus cosine squared theta is equal to 1, and we can obtain two others of a similar form by dividing by either cosine squared theta or sine squared theta. The Pythagorean identity appears pretty frequently, so it is definitely worth being familiar with all three forms of it. Unfortunately, we're going to have to move away from the unit circle and into equation land. The sum difference identities are one of the most basic ones, where it is able to simplify a trig function whose angle is the sum of two other angles or the difference of two angles. For example, here is the sine sum identity, and here is the sine difference identity. We can combine the two into one unified form. Similarly, here is cosine sum identity, and here is its difference identity. And once more, we can combine it together into one form. And of course, don't forget for tangent. Now, it is important to note the distinction between plus minus and these minus plus symbols. In the sine case, the two plus minus symbols indicate the two cases where either both symbols are pluses or both are minuses. However, in the cosine, the plus, minus, and minus plus symbols indicate the two cases where while one is a plus symbol, the other must be a minus symbol. Some difference identities are definitely worth memorizing since they are so fundamental to other identities that we will learn. Taking these sum identities from before, let alpha equal beta. When we do this, we derive the double angle identities, where a trig function is taken two times an angle and simplify it into a single angle. Now, the sine and tangent double angle formulas aren't really that interesting. The one we really want to keep an eye on is the cosine double angle identity, because it involves the square of cosine and sine. So we might be able to use the Pythagorean identities there. And we can see after a little rearranging and adding to our equation, we indeed see that cosine of 2 alpha is equal to 2 cosine squared alpha minus 1. And if we subtract the Pythagorean identity, then we can also see that cosine of 2 alpha is equal to 1 minus 2 sine squared alpha. These three forms of the cosine double angle formula appear countless times in trig identity problems, and they're even more useful to derive even more identities. There are other trig identities, but they're out of the scope for CAML. If you'd like to see them, I'll leave a link below to a sheet of all trig identities. Some problems may require you to solve for the angle theta within a trig function. For that, we need to know specific values for the trig functions. We only need to know the functions of sine and cosine because any trig function can be expressed in terms of sine and cosine. And we only need to know the values of the degrees 0, 15, 30, 45, 60, and 90 because we can apply our reduction identities to obtain any other angle measure we want. Some trig problems might try to trip you up by using a different unit for angle measure. Usually we use degrees, but some problems might use radians. The only difference is that radians tracks the length of the arc subtended by the angle theta in the unit circle. For example, we know that there are 360 degrees in the whole circle, and the arc length of the whole circle is 2 pi. So 360 degrees is equivalent to 2 pi radians. Similarly, 180 degrees is equal to pi radians, 90 degrees is equal to pi half radians, and I think you get the idea. Now let's cover a few examples on the application of these identities. I can't cover every single kind of problem that you might encounter, but the problem set linked in the description below should do an adequate job. Problem 1. Simplify the following expression in terms of sine of x. You see that our expression is the product of 4 terms, all of which are in radians. If you need to, you can convert the radians into degrees. We might recognize that we need to apply our reduction identities here. So let's break this down term by term. We can see on the unit circle that sine of pi halves minus x is equal to cosine of x. If we substitute that value in, how about cosine of pi minus x? Recall that pi minus x is the same as reflecting our point P across the y-axis. So cosine of pi minus x is equal to negative cosine of x. Let's substitute that in. Cotangent of 3 pi halves minus x is equal to cotangent of pi halves minus x because of the pi radians rotation, which is equal to tangent of x. Let's substitute that in once more. And the final term, tangent of 2 pi minus x, because that's a rotation by 2 pi, that's equal to tangent of negative x. Now, negative x is a reflection of point P across the x-axis, so this action negates the slope of the radius to P, which means that we have negative tangent of x. Notice how we've simplified all of our expressions in terms of just the angle x and nothing extra. So let's combine our terms. It might seem like we're stuck, but remember that we can express tangent in terms of sine and cosine. Let's do exactly that. And we can cancel the cosine squared x's, and we're left with our final expression, sine squared x. Problem 2. Find the smallest positive x such that Analyzing the situation, we can see that we have an equation this time, and on the left-hand side, we have the trig functions. It looks like the two terms on that side have a common factor, so let's try to factor it out, like we do with a regular equation. Factoring out the sine and cosine from the left side, we can further factor the right term as a difference of squares. Perhaps our final goal might be to have a single trigonomic expression left in our equation, so that we can easily find the angle x. Now that we have broken our left-hand side into the product of terms, let's simplify each term separately like we did in the previous problem. Now 8 sine x cosine x, that looks like the sine double angle formula because it involves sine times cosine x. Let's substitute that in. Looking at the second term, cosine squared x minus sine squared x looks like the cosine double angle formula. Let's substitute cosine 2x. And the third term, cosine squared x plus sine squared x, that looks like the Pythagorean identity. Let's substitute a 1 into there. Since we're multiplying sine and cosine together like this, maybe we can apply the double angle formula for sine. And in fact we can, not starting with x this time, but with 2x. Let's substitute sine of 4x in. Then we should also try to find the smallest positive 4 times x in this expression. Going back to our specific list of values, the smallest positive 4x would be sine of 60 degrees. So 4x is equal to 60 degrees, and x equals 15 degrees. Simplify the following as a non-fractional monomial. So it appears that we already have an expression of the sum of two simplified trig functions. How can we even go forward and simplify this into a single term? Well, consider this. If we want to have a chance to combine the two terms together, we first need to have their angles be the same. We need to half the 10 into a 5. So let's convert to tangent. Then we can apply tangent's double angle formula. We have a fraction of refraction, so let's simplify. And then we can combine with a common denominator. It looks like the top 1 plus tangent squared 5 radian could be used from the Pythagorean identity. 1 plus tangent squared 5 equals secant squared 5. So let's substitute the secant squared 5 and see if we can cancel anything out. Although it might not appear we can always pull a trump card, converting into sine and cosine. Doing so and simplifying and canceling out, we have a sine multiplying by cosine. That looks like the sine double angle formula. So now we have 1 over sine of 10. Oh, we can't have a fraction for our answer, so we simplify into cosecant of 10. Okay, so the round of trig identities is all about memorizing identities, applying them to manipulate the expressions they provide. We have some useful tools that we can use in the round. For example, the unit circle model, which remains flexible for us to derive so many reduction identities. Now, regarding CAML specifically, the important identities to learn are the basic identities, the Pythagorean identities, the sum difference identities, the cosine double angle identities, and as well as the reduction identities from the unit circle. And it's also helpful to learn some values of sine and cosine in case you need to solve for the angle theta within the trig functions, as well as the unit radians, which they might throw at you. And of course, remember to ling ling 40 hour.